Hello everyone, today I am going to start this topic of a diffraction from the chapter Wave Optics and for the class 12th Physics. Let's begin. Here I had taken a slit S, which is the source of a light by which the light starts to emit. Here is an obstacle by which a geometrical shadow is formed. Now the illumination is because of that obstacle, the image must be formed in a spot form. But what will be happen if the slits have two obstacles? It will be diffracted, and we have get two different types of a shadow. The bending of a light is the nearby edges at the corner of an obstacle or the slit and is spreading into the region of geometrical shadow is known as diffraction of a light. Or simply we can say the bending of a light beam at sharp edges is known as diffraction of a light. So types of a diffraction, if I'm just taking Fraunhofer diffraction and Fresnel diffraction. In a Fraunhofer diffraction, the source of a light and the screen on which diffraction pattern is obtained are effectively at infinite distance from the diffracting system. In this case, diffraction pattern is obtained by using convex lens. We consider a plane wavefront in this case, whereas in the Fresnel diffraction, the source of a light and the screen are kept at a finite distance from the diffracting system. In this case, we consider cylindrical or spherical wavefront. In a Fraunhofer, plane wavefront, and Fresnel, cylindrical and spherical wavefront is formed. Now let's move with the question. The bending of a light from the side corners of an obstacle is called as interference, diffraction, reflection, or refraction. The correct answer for this question is diffraction. Next question. In a Fraunhofer diffraction and the diffraction pattern is obtained by spherical wavefront, plane wavefront, cylindrical wavefront, or circular wavefront. The correct answer is a plane wavefront. Now, let's see the Fraunhofer single slit experiment. Here we have taken convex lens and the lights are passes which is a parallel to the principal axis after conversing because convex lens is known as conversing lens. So, this will be converges at point focus. Now, because of the obstacle, light rays little bit deviate from its own path and the image formed at this pattern. So diffraction pattern consists of central large maxima, alternate maxima and minima. Entire pattern is very complex with less contrast. So let's move with some questions. In Fraunhofer diffraction, we get the diffracted pattern by concave lens, convex lens, mirror or a glass slab. The correct answer is a convex lens. In a Fraunhofer diffraction, we get the alternate maxima minima, waxing waning, large sound or a beat. The correct answer is a maxima and minima. Variation of intensity in the slit single diffraction. So variation, different kind of intensities, means a layer of intensity we will actually get from this experiment. So variation of intensity in a single slit diffraction will be like this. So there is a intensity pattern which is a lambda by A, 2 lambda by A, 3 lambda by A or a 5 lambda by A in the positive form, and in the negative side minus lambda by A, minus 2 lambda by A, minus 3 lambda by A, minus 4 lambda by A and minus 5 lambda by A. The intensity ratio, as you can see students, the equi-pattern form in this ratio. Whereas at the mid there is a central maximum Then after first, this is the first maxima, second maxima, third, and a fourth maxima. Case 1, if S is equals to D, it means the separation between the central maxima of 2. We can easily deduct. Object is just equals to the distance between the central maxima. And the first minima of any of the object like this. In this case, two objects is such that they are just resolved. In a case 2, when S is a greater than D, it means separation of the central maxima of the two objects is greater than the distance between the central maxima. Because of that, we can say the first minimum of any of the object, in this case, two objects is called as well resolved. But if S is a less than D, means the separation between the central maxima of the two objects in less than the distance between the central maxima and the first maximum of any two objects. In this case, the two objects are just unresolved. We can't separate these two things. So as you can see, students, here, this S is really so much less between the D. Because of that, they are like the peaks. If we are just saying actually from the outer side, it will be like looking as if that just overlap. They are just doing overlap with each other. In the previous case, as you can see, students, if I'm just taking the gaps, so in between we have a two maximum. If I'm just taking the previous one also, so here, as you can, they are just resolved. Okay, like the first one only enter in the section. In the second case, the two, and in the third case, they are unresolved. After seeing this experiment, there are many scientists which is researching on this particular topic, in which there are among of this a single scientist. There will be one of them is a Rayleigh criterion. So Rayleigh gave his statement: the image of a two-point object close to the each other are regarded as just separated if the central maximum of one diffraction pattern falls on the first minimum of the other diffraction pattern. Now we'll take some MCQ questions. The two patterns of a diffraction are just said to be unresolved if diffraction pattern of a central maxima of the one pattern coincide with the first maxima. Central maxima of the one pattern does not coincide with the first minima. Central maxima of the one pattern sometimes coincide with the first minima, and none of these. The correct answer is first, the central maxima of the first pattern coincide with the first minima of them. Second question we have: when the distance of a coincidence for two diffraction pattern is a less than Rayleigh criteria, then the pattern is known as a well resolved, unresolved, just resolved, or none of these. The correct answer is unresolved. Now distinguish between the interference and diffraction little bit. So earlier we studied the interference, and like now we did diffraction completely. Interference and diffraction. The first point which we observed, the superposition of the waves takes place band, like bright band and dark band in the form. And superposition of a waves takes place in the form of maxima and minima. All bright bands have the same intensity. But whenever we are taking about the diffraction pattern, the intensity ratios are changed. We will get a maxima and minima, and the amplitude module will be sometimes less and sometimes we can say high in this scenario. So for that scenario, we can say they all are not same actually. Central bright band are the highest intensity and move away the intensity where the maxima have actually in the decreasing form. The size of every fringes is same. The size of the central maxima is larger than the other maxima. Here the resolving power of the optical instrument doesn't depend on the phenomena of light, but here resolving power of the optical instrument depends on the diffraction of light. So I hope by these 4 points you will be aware that what is the difference between the interference and diffraction. Bandwidth, like here bright band and dark band, here maxima minima. Intensities are same here, but intensities varies here. Interference size of the fringe is same, but here the larger and as we can say bright band and like fringe bits will be same, but here because of the maxima and minima we can say that this will be different in size. And resolving power, as I told you, it depends on not depends on the optical instrument, but it depends. Now let's move on to some questions. The intensity of the bright band in the interference pattern is same for all bands, maximum for the central band, minimum for the central band, and none of these. The correct answer for this question is same for all. The diffraction pattern size of the central maximum is more than the other maxima, same as the other maxima, less than the other maxima, or none of these. The correct answer is more than the other maxima. If you remember the pattern, students, so we are like this. Okay, so this is a central, and in the central point, the maxima will be more. Now let's take the resolving power concept. When two objects of their images are very close to each other, they appear actually at the one. It may not be possible for eye to see them separate when the two objects of images are very close. But if they are if the object is not seen separately, then we say that details are not resolved by the eyes. And optical instruments are assist the eye's resolving power by the images. So the method adopted to see the close object to see the object separation, that is called resolution. And the ability of an optical instrument to produce actually distinctly separate images of two objects is located very close to each other is called resolving power. Like for more information, students, if I'm just taking example of a car. So car have two headlights, and if the car is a very like far from you, so you can obviously you can see that both headlights, but as soon as they will be nearby you, you will be can't like resolve that the intensity of a both because of the high intensities. Same concept we will apply here. If the distance between both the sides, like small d, is a large in size, that is we are saying that they are just resolved. We use the resolving term to different senses. First, in the case of microscope and telescope, we will take geometrical resolution, where the geometrical position of two nearby objects is resolved. In the case of spectroscope, we refer to spectral resolution, where differences of a wavelength of a light in a given source are to be resolved. Resolving power is basically defined as the reciprocal of the smallest angle sustained by the objective of the optical instrument by the two-point object, which can be just distinguished by the separation. If I'm talking about the limit of resolution, so the minimum separation from each so that their images are produced, by microscope are just separate is called as a limit of a resolution. Resolving power is equals to 1 by limit of a resolution d. And resolving power of microscope is defined as the least distance between the two resolved object point is given by limit of a resolution d is equals to 1.22 lambda by 2 mu sine theta, where mu is equals to refractive index of the medium in which the object is placed. Theta is a semi-vertical angle or half angle sustained by the lens. Lambda is equals to average wavelength. So the resolving power is a 1 by d. That means 2 mu sine theta divided by lambda. Let's take some questions. So resolving power of a microscope is given as d is equals to 2 mu lambda by sine theta. D is equals to 1.2 mu lambda by sine theta and D is equals to 1.22 lambda by 2 mu sine theta, or D is equals to 2 lambda by sine theta. The correct answer for this question is D is equals to 1.22 lambda by 2 mu sine theta. The least distance between the two just resolved object point is directly proportional to wavelength of light, refractive index of a light, angle of incidence, none of these. The correct answer for this question is the wavelength of light. Resolving power for a telescope. So, the magnifying power of a telescope is given by dm is equals to d by d, where d is the diameter of the objective or in-phase pupil and d is the diameter of the axis pupil. The magnification of a telescope is said to be normal if d diameter axis pupil is equals to de, that means diameter of pupil I. Therefore, normal magnification telescope is a d by d. Further, if the limit is extended or we are just taking the limit of resolution of a telescope is given by d theta is equals to 1.22 lambda by d. And limit of resolution of our eyes is that d theta is equals to 1.22 lambda by de. From equation we can say d theta prime by d theta, that is equals to limit of a resolution of the eye divided by limit of the resolution of the telescope. So after solution we will get m. Thus the product of a normal magnification power or a magnifying power of the telescope and its limit of a resolution is equals to the limit of a resolution of the unadded eye. Now let's take some master's MCQ question. Like resolving power of a telescope is 1 by d theta is equals to a by 1.22 lambda. 1 by d theta is equals to lambda by 1.22 d. D theta is equals to d square by d and d theta is equals to d by d. The correct answer is A. Resolving power of a telescope is directly proportional to the lambda. Inversely proportional to the lambda, not depend on the lambda, none of these. The correct answer is it is inversely proportional to the lambda. Student, this is all much for the today's class. I hope you learned many things. So, thank you for watching this video.